Hello, my name is Juancho A. Collera. I'm from the Department of Mathematics and Computer Science of the University of the Philippines, Baguio. And today I'll be talking about bifurcations in cryptocurrency model with government intervention. By the way, this research is a joint work with Gamboa, Sahagun, and Passion. Okay, so for the outline of my talk, I will first introduce the proposed cryptocurrency model with government intervention. And then we're going to examine the local asymptotic stability of the unique equilibrium, then derive the conditions for Hopf bifurcation. We're going also to explore further dynamics via numerical simulations. And then finally, we interpret the results. Okay, so for the proposed model with government intervention, so basically, the one given here generalizes the work of Kaginalp by incorporating the government intervention through a tax rate parameter G. Okay. So here the state variables are P, the trading price, P sub A, the perceived value, L, the liquidity price, zeta 1, the trend component of the sentiment, and zeta 2, the value component of the sentiment. So the following equations are actually derived using what we call asset flow equations. And actually for the second, third, fourth, and fifth equations, these are initially delay equations but are written now in terms of the derivatives. Uh, for sake of brevity, we refer to the work of Kaginals for more details on the parameter description, values, and assumptions. In terms of equilibrium, so the system has a unique equilibrium given by A star. So the expression for the equilibrium is given here. So you can actually obtain this equilibrium by solving the following system of equations. For example, if you look at the second equation, you get the trading price equal to the uh, perceived value. And if this is 0, then you do get this term here on the fifth equation equal to 0, and zeta 2 is also 0. And then the first equation, if this quantity in the square braces is 0, then you do get these quantities in square braces in the third and fourth equations also equal to 0. For example, for the third equation, you do get the liquidity price equal to this L naught. And for the fourth equation, if this one is 0, then you do get the trend component of the sentiment also equal to 0. So at the end of the day, you're going to get this unique equilibrium point. So here, both the sentiments are equal to 0. The liquidity price is equal to this baseline value, and the trading price has to match the perceived value of the asset. So in terms of local asymptotic stability, so we do have the following theorem. So the equilibrium E star is locally asymptotically stable provided you satisfy the following two conditions. So basically, these conditions are obtained through the Routh-Hurwitz criteria. And just to mention, the coefficients A, B, and C here are actually dependent on the value of the tax rate G. So if you change the value of G, then you're also changing the value of these coefficients A, B, and C, and you need to check if still those will satisfy the asymptotic stability conditions. Okay, let's look at this particular example. So the one on the left-hand side, the value for the tax rate is 0.05. Apparently, this implies that A, the coefficient A, is positive and AB is greater than C. So basically, these are the conditions from the previous theorem, and this implies that E star is locally asymptotically stable as depicted in this time series plot. In contrast, for the figure on the right, the G is 0.25. So we increase it from 0.05 to 0.25. Apparently, this implies that the second condition is violated. And actually, E star here is unstable. So based on this example, we have two observations. One, if you increase the tax rate G, this may cause a stable equilibrium to become unstable. So if you're going to look at the figures. And then second, the switch towards instability can be due to the Hopf bifurcation, and it will occur at some threshold value G star. So you can see here the switch instability actually also gives you like this oscillation, and apparently this oscillation is due to the Hopf bifurcation occurring at G star. So this suggests we look at or we examine the system in terms of Hopf bifurcation. So the conditions for Hopf bifurcation to occur given by this theorem, in particular in item B. So here we have basically we have two conditions for Hopf bifurcation to occur. So the first condition actually, uh, it guarantees you that you do get these purely imaginary roots of the characteristic equation corresponding to the linearized system at E star. And the second condition is actually just the transversality condition. So if you're going to look at this figure, so we see that it's the branch of equilibria and it is obtained by varying G. So if you change your G, you do get different equilibria, and then if you compile them, you do get this branch of equilibria. And apparently this asterisk here, it indicates the occurrence of Hopf bifurcation. And in particular, it occurs when G is around 0.2037. Before the Hopf bifurcation, the unique equilibrium is stable, locally asymptotically stable. However, beyond the value of G, the equilibrium becomes unstable. And the reason being is the following. So if G is less than G star, then you satisfy this condition for stability. So you do get a stable branch of equilibria. However, once you hit G, you get a purely imaginary characteristic roots. And eventually, if you further increase G greater than G star, then you do get instability. So what it means is uh, those characteristic equations that are in the imaginary axis when G equal to G star will move to the open right hand of the complex plane. And therefore, you do get this stability switch towards instability. Okay, so we also explore further using numerical simulations. So in particular here, we use the software MathCont. So the figure here actually gives you the Hopf bifurcation curves. And these Hopf bifurcation curves in blue, it partitions the parameter space into two. So the shaded region is the stable region, and then the unshaded is unstable. So if you pick your G and Q on the shaded region, the values of those two parameters, then the equilibrium is stable, locally asymptotically stable. But if you pick your value of G and Q outside that shaded region, then it's unstable. So what do we see here? In order to get stability, the value of the parameter Q, similarly, the value of the parameter Q1 has to be small enough. If these values are large, then you do get instability. And actually, this observation can also be can also get it through the equations. So, for example, in this L equation, if Q is small, for example, 0, then you do get the liquidity price equal to you do get the liquidity price closer to the baseline value L naught. And similarly, if Q1 is small, say for example this term here will be 0, then you do get like a exponential decay, and therefore this theta 1, the trend component of the sentiment, approaching 0. and therefore it makes the equilibrium more stable. Okay, so let's look at another diagram. So here, again, we also have the Hopf bifurcation curves, and then again, it partitions the parameter space into stable and unstable regions. So this picture here actually tells us that for low to moderate government intervention, so when G is low to moderate, then it can sustain stability. However, if G is large, you do get to this unstable regime. And actually, when G is large, then you do get this excessive regulation. So if you have excessive regulation combined with mispricing, so mispricing we mean by the trading price is actually quite different to the perceived value, then this causes destabilization of the market. And based on this result, we suggest the following: that the regulation should be flexible rather than a one size fits all. Lastly, we look at this bifurcation diagram in G versus tau 0 parameter. So if you will recall, tau 0, it determines the time scale between the imbalance in supply and demand and the corresponding price change. So when the market adjusts quickly, so in other words, when tau 0 is small, so if you're going to look at this picture, tau 0 is small, then the government intervention helps to stabilize prices. In contrast, when the market adjustment is slow, so in other words, when tau 0 is high, so you do get a high value for tau 0, for example, at this point, then even a moderate intervention can trigger instability and persistent volatility. So if you're somewhere here and if you increase your G, then it could cause instability and persistent volatility. So to conclude, the effectiveness of government policies and intervention depends strongly on how fast the currency market reacts. And to summarize, in this work, we introduce a cryptocurrency model with government intervention in the form of a tax rate. So this model basically generalizes the previous work of Kaginalt. And our main results include conditions for local asymptotic stability of the unique equilibrium, as well as conditions for Hopf bifurcation to occur. And together with these theoretical results, combined with the numerical simulations, it allows us to gain insights on the effects of government intervention on stability and instability of cryptocurrency. So particularly, we have the following recommendation. We saw that excessive regulation can be destabilizing, and therefore one suggestion is to have more flexible government policies and interventions. And lastly, let me just thank the organizers of the 14th International Conference on Mathematical Modeling in the Physical Sciences, my university and my research group. And also would like to mention that this work supports the UN Sustainable Development Goals, particularly on quality education, decent work and economic growth, and partnerships for goals. Thank you so much.